Welcome back to the Deep Dive. We are cutting through the noise to bring you the highest level synthesis of cutting-edge research. Today we're doing a deep dive into the architecture and the implications of a paper titled Emergent Temporal Abstractions in Autoregressive Models Enable Hierarchical Reinforcement Learning.
This is a really breakthrough piece of research. Our mission today is to give you, the expert listener, a comprehensive overview of this fascinating concept they're calling internal RL. We're going to look at how autoregressive models, the transformers, the state space models that power modern AI, can be fundamentally repurposed for efficient hierarchical reinforcement learning.
HRL.
Right, HRL. And it's done simply by allowing an external controller to operate within the model's own internal activation space.
Okay, let's unpack this. We've all seen the successes of foundation models fine-tuned with RL, but there's a hard limit. When we try to apply them to tasks that need long horizon planning, sparse rewards, think of a robot that has to do a long sequence of steps before it gets any feedback at all.
Yeah, it just fails.
Standard token-by-token RL utterly fails. Exploration is inefficient, and credit assignment becomes basically impossible.
Exactly. The root of the problem is this granularity mismatch. If you're acting at the level of individual motor commands or, single output tokens, you just can't learn reusable subroutines.
Which is the entire point of hierarchical RL.
Precisely. The paper's central hypothesis is that the model implicitly learns these necessary temporal abstractions during its initial self-supervised pre-training.
So just from next token prediction.
Just from next token prediction. They're just hidden deep inside the transformer structure, specifically in the residual stream.
So the goal isn't to force the model to generate abstract actions in the output, but to find where the intention to perform those actions is encoded internally, and then build a system to sequence those intentions.
You've got it. The research systematically tackles this in three really distinct verifiable phases. First, just establishing that the abstract representations even exist, via probing. Second, introducing an unsupervised metacontroller to discover and then sequence these latent intentions or actions. And then finally, deploying the full internal RL policy to solve these hard, sparse reward tasks.
And for this deep dive, we're going to stick strictly to the results presented across those three phases.
That's the plan.
All right, let's jump into phase I then, confirming the hypothesis that next action predictors inherently develop these temporally abstract action representations. What was the setup for testing this?
Well, the setup was elegant because it relied entirely on behavioral pre-training. They used both standard transformers for symbolic environments and state space models like Hawk for the continuous ones, and they trained them on these large data sets of observation action sequences generated by expert agents solving really complex compositional tasks.
We're talking about two very different environments here, right? A discrete grid world pin pad task, which is symbolic,
right,
and a continuous control task using the MuJoCo ant robot.
That's right. And the ant pinpad task, that requires the model to implicitly encode this complex, continuous joint-level control. The grid world is, much simpler movement. But the critical point, and this is really key, is that the behavioral datasets contained no explicit rewards.
No labels at all.
No labels, no goals, no sub-goal markers, nothing. The model was only trained to predict the next token or the next action based on history.
So if the model is only predicting the very next step, how did they prove it was internally thinking ahead to some multi-step goal?
They used linear probing. They took the instantaneous internal activation vector, you can think of it as the model's belief state, from the residual stream at different time steps and layer depths.
Okay.
Then they trained a simple linear decoder to predict the ground truth abstract subgoal, the subgoal that was, of course, known only to the researchers, not to the model.
And what were the probing results? What did they find?
What's fascinating here is this gradient of confidence. The probability mass assigned by the decoder, it concentrated on the correct latent subgoal as the trajectory progressed.
So it got more confident over time.
Yes, the model became more confident the closer the agent got to realizing that implicit goal. And crucially, this confidence also increased with layer depth, peaking right near the final embedding layer.
So that confirmed it. Despite a really short horizon, one-step prediction objective, the model developed a temporally abstract belief state that evolved over time.
Exactly. It verifies the existence of the representation.
Okay, so that's step one. The next, and I'd argue harder, step is proving controllability. It's one thing to decode the belief state. It's a whole other thing to intervene and actually steer it.
Absolutely. So they introduced a simple low-rank linear controller. just a subtle intervention vector into the residual stream between model blocks. And initially, this controller was steered using the ground truth subgoal labels, just to see if they can manually activate specific behaviors.
And this is where it gets really interesting for me. Why is the optimal insertion point for this control vector near the mid-depth? I mean, if the final layer holds the most refined belief state, shouldn't control be easiest right before the output?
That's a great question, and it speaks directly to the difference between representation and control. The final layers might perfectly decode the agent's current implicit goal, but intervening there, it's like shouting at the conductor just as the music is ending.
Huh? Right, too late.
It's too late. Intervening near the final embedding just forces a disruptive change on the raw action token. The mid-depth, however, that's where the model is actively processing and shaping the sequence of latent features that are going to drive the behavior.
So by inserting the controller in the middle, they're able to modify the high-level thought process before it resolves into concrete action tokens.
Precisely. And the evaluation on out-of-distribution tasks, novel combinations, longer trajectories, it showed that inserting the controller near the mid-depth maximized compositional generalization and success rates.
And that was true across both the symbolic grid world and the complex, continuous Annan environment.
It was. So this confirms that this mid-layer region is the most malleable point for abstract control.
Okay, so if phase I confirmed the abstraction exists and proved we could control it with a manual ground truth signal, phase II was the big engineering challenge. How do you automate the discovery and sequencing of these abstract actions without any supervision? This is where the metacontroller comes in.
Right. This is the major architectural innovation. The metacontroller is a generative recurrent hypernetwork. It's designed specifically to approximate the sequencing of functional intent. It's an encoder-decoder that generates that low-rank controller vector that intervenes in the frozen AR model.
Let's break down the two features that are really essential for discovering this temporal abstraction. The first one is its unique conditioning.
Yes. The metacontroller's encoder is non-causal.
Meaning it can see the future.
Essentially, yes. It looks at the latent activity of the entire sequence, or at least a large window of the future, to determine the abstract action at the current step. Think of it like this. If you only look at one frame of a tennis match, you can't tell if the player is serving, receiving, or celebrating. You need the whole sequence to infer the goal.
That makes perfect sense. It needs context beyond just the current time step to know if the agent is halfway through go to the blue door or just starting pick up the key. So what's the second feature?
The second is the temporal integration mechanism. They use a recurrent switching unit that produces a continuous switching gate, we can call it beta, which is a value between 0 and 1.
Okay.
And this beta value dictates how much of the new proposed abstract action code is mixed in with the previous one. If beta is close to 1, the system switches to a new abstract action. If it's close to 0, it just maintains the current one.
And that mechanism inherently encourages sparse variable switching.
Exactly.
And the training objective here was self-supervised. It included a next action prediction loss, but critically, also a KL divergence regularizer on the controller codes, a classic rate distortion constraint.
Which leads us to probably the most critical optimization finding of the entire paper. The necessity of freezing the base AR model parameters, theta, while you're training the metacontroller parameters, phi. This freezing step, it's not just a technical preference. It is a fundamental architectural separation of concerns.
What happens if you try to optimize both at the same time?
You get degenerate solutions immediately. The rate distortion analysis showed that when the parameters were jointly optimized, the system just converged to a single switch. It collapsed the entire sequence into one long abstract action.
So it lost all the temporal structure.
It lost everything. By freezing the AR model, they established a hard boundary. The foundation model's representation is locked in, and the metacontroller must learn to interface with that locked-in structure, not destroy it.
That separation of perception and control is the key architectural takeaway. And the result?
The result was that the metacontroller successfully learned to segment time. The continuous switching gate, it started behaving in this quasi-binary, sparsely switching fashion. It perfectly recovered the ground truth abstract action switching times.
Despite having no explicit instruction to do so.
None at all. Which confirms successful, unsupervised discovery of functional intent. It proves that the latent controller codes it generated, what we can call the abstract action space, truly correspond to meaningful, temporally abstract actions. And that hands us the essential primitive for phase 3.
Which brings us to the payoff. Phase 3, internal reinforcement learning. Finally, addressing the initial problem of sparse reward, long horizon exploration.
The internal RL paradigm is it's a neat conceptual trick. We treat the frozen autoregressive model, the perception system, plus the controller-decoder part of the metacontroller, we treat that whole thing as the environment.
Okay, so it's all internal to the model.
It is. Our new RL policy operates on a contracted timescale. It uses the internal activation vectors as its observations, and the abstract controller pods, the command space, as its actions.
So instead of predicting the next token, the policy is now predicting the next high-level command. And to align with that abstract timescale, they binarize the continuous switching rate using a simple threshold.
Yes, and the results comparison is just a stark illustration of how effective this approach is. Let's look at the baselines. Standard post-training RL, even using robust methods like GRPO,
Right.
and the existing hierarchical method compiled, they failed, utterly. On these sparse reward tasks, they achieved near zero success rates.
Even when allowed up to 1 million training episodes.
1 million episodes.
1 million episodes resulting in zero success. That's not just slow learning. That's a total principal failure of token-level exploration in a sparse space.
Precisely. They just couldn't find the signal. And what's more, internal RL ablations, for instance, forcing a switch at every single time step, which removes the temporal abstraction benefit, that also failed to perform efficient credit assignment.
So it shows that having the right action space isn't enough. You need the temporally abstract action space and the contracted timescale.
You need both.
But the full internal RL algorithm.
The full algorithm achieved high success rates and did it rapidly. On the grid world, it learned the tasks successfully within 60 to 80,000 episodes, outperforming the baselines by orders of magnitude. This overwhelming efficiency gain is the critical result. It confirms the value of latent action generation and reinforcement in AR models for these really hard tasks.
So let's synthesize the whole picture here. This deep dive reveals a really powerful three-step pipeline. The autoregressive pre-training inadvertently forces the model to encode these temporal abstractions internally. Then, by freezing that base model and training a separate future-conditioned metacontroller to learn the sequencing of these internal interventions, the system acquires a robust hierarchy that standard sequential RL just cannot leverage.
The efficiency gain is monumental. And it's not just about better exploration. The core mechanism is the drastically simplified credit assignment because of the shortened effective time horizon in that abstract command space.
Right, fewer decisions to make.
Way fewer. When you move from making thousands of decisions to making, dozens of high-level command decisions over a trajectory, the policy gradient variance is fundamentally reduced. Every single learning step becomes exponentially cleaner and more informative.
This research really offers a profound structural insight into how we might leverage foundational models for goal-directed behavior.
It does, and if we connect this to the bigger picture, it suggests a powerful general paradigm for combining self-supervised representation learning with reinforcement learning. Which brings us to an important question for you, our expert audience. If we can prove that using internal abstract actions fundamentally simplifies credit assignment for foundation models, does this mean that multi-step reasoning in massive general-purpose LLMs is fundamentally an HRL problem disguised as next token prediction? Think about the implications of viewing complex reasoning not as generating text, but as sequencing internal temporally abstract commands. What could we unlock with that perspective?